Our first speaker today is Peter Broadwell from the Stanford University. Peter's been with the university now for some 5 years, and they're doing a lot of works. As we've heard, Stanford is archiving the Condon collection. They have a large collection of rolls, and I'm very much encouraging that they continue this work. And Peter's been working for some time on a virtual instrument, and this allows people to access this instrument through the internet. And he will demonstrate that today. We'll be hearing more of that on the disc clavier. But Peter's talk right now is a little bit more about the processes of emulation. You've heard a bit already, and Peter's doing some extra work which is taken on. It was originally begun by Kitty Shee at the university, and it's now being carried on by Peter. So without any further thing, just one thing I do want to say before we let Peter loose. We're trying to keep to a tight schedule. The reason being, if we don't, your lunch will be cold. Peter Broadwell.
Thank you so much, Peter. I think we're getting a bit of a ring. Maybe it's from this. Yeah. Okay. Okay. Well, great. Thank you again, Peter, for that introduction. It's wonderful to be here in this amazingly, definitely the most impressive renovation of a former equestrian facility that I've ever seen. Although I have for recollection that the venue for the Baron piano roll meeting 2 years ago was also perhaps in a converted cavalry stables. And well, the Stanford University, all of it at one time was a horse farm owned by Leland Stanford. So I think we're developing a theme there. Anyway, so yes, I will be talking, as the first half of my title indicates, about using some data science methods to refine our player piano emulator, particularly with trying some new to me and hopefully new to other folks techniques for comparing roll scans to that is scans of the player piano rolls to recordings of those same rolls being played on reproducing pianos primarily. Although I should mention I am mostly talking about Welte, Mignon, expression emulation techniques, but also there'll be some discussions of slightly lower level features that actually can apply to any player piano, including just basic pianola systems like we have outside for people to try out. But yeah, my primary responsibility has been to continue the work of emulating and building a player to access all of the rolls that piano rolls that the Stanford Libraries has collected, including the great gift of the Condon collection. But this is continuing work that was begun by many people, and several of whom are here as well, as Peter Phillips also mentioned. And I'll just also give a shout out to my team and the other people in the library who I've been working with on a lot of this work, particularly the Pianolatron emulator, which you'll see Kumaran demo later on. I really won't be demonstrating it specifically, but I'll be showing some of the work that has led to its basically how it has been configured. Okay, so I do mention data science in the title of my talk. You may be wondering what that is exactly. It's kind of an intentionally vague term that I chose intentionally because it's vague. It's perhaps one of the few terms that's less informative than computer science in describing an actual field. But you can see here from all these Venn diagrams that there's a bit of statistics involved. I love this one on the left that just mentions basic mathematics, not advanced mathematics. Machine learning, data visualization, these things. So I think you'll see, hopefully we'll see, so it's in the middle of a Venn diagram. But I think we'll see how this is kind of a useful framing device just because for the Stanford Piano Roll program, for the Supra collection, we are having to work at scale on thousands of rolls. We need techniques that generally don't require intervention at the level of a single roll. We need and when intervention is necessary, we want to know. We want the software to tell us that a roll has not been scanned properly or is not being rendered properly, but we also can't afford to check each one by hand. And so that's where data science comes in as well. But also, one silver lining to that setup is that we have a lot of data to work with, which can inform some of our decisions about how the emulator, how the player system itself is actually set up. So I'm going to be talking about that a bit. It might get into the weeds with details a little bit, but I have lots of pictures, so maybe that will help to smooth things over. Speaking of smoothing, I'll just describe some successes that arguably derived from data science techniques. So one approach is when you're using when you're doing scanning of the roles and detecting, the holes in the player roles visually. You don't necessarily know where the tracker should go. All we're pretty much guaranteed to know is that the holes will be somewhere in the image. They're pretty easy to find because they're white on black or black on white, or on tan in this case. But the actual vertical columns that we need to know to assign notes and expression roles to those holes need to be inferred. And so I can't claim credit for any of this. This is Craig's work. He came up with the idea of just building this histogram basically of where the centroids, of where the most holes appear on the page, and measuring the distance between those columns, and then applying a Fourier transform to determine the fundamental spacing of the tracker holes. We know that we generally know these are like 9 hole per inch rolls. We should know where the tracker holes are, but in practice, it's not actually that easy. So this is an approach that helps us to kind of really zero in on the locations of the notes. But things can still go wrong. So this is one case where data science helps us. So occasionally, the harmonic profile of a roll will result in a false peak in our Fourier transform. So this is not where we should be determining the interhole. This is not the correct intercolumn distance. It's that one. And so this is if we just went with the sort of the raw results, we get the roll that sounds really strange. I'm sorry, I should have had the audio to play for you, but imagine just like atonal music played on a player piano. But fortunately, it's pretty easy to fix. You just apply smoothing to that histogram, and it brings out the proper distance and allows you to assign. In this case, this is what the app has coloration for different velocity, volume levels for the treble and bass. There's the green highlighting indicates expression holes. So this is that's all working correctly. So that was one success. Another success was determining the optimal hole bridging distance. We had a great talk just recently discussing some of these issues as it relates to different piano roll technologies. Red Welte is particularly a problem because, as Craig mentioned, there is no punch grid as we recognize it for other later roll types. And so we do occasionally get problems even just making assumptions about what the optimal distances between repeated key strikes versus continuations. And it's particularly bad when you're talking about, in this case, Schubert's Erl King, which was famous for that. So if we don't choose the right distance, we get it doesn't sound like the piece. In this case, we do some other build some other histograms of the interhole distances and just apply some heuristics to sort of fine tune the settings that we're using. To get the right bridging, and this is the result. So again, previously we were sort of dialing in the vertical spacing to assign the correct notes and expression roles, and now we're sort of dialing in the you could say the horizontal spacing, or you could think about it the other way around. We're working with the two dimensions that we have to work with. All right, so those are some previous wins, and so now I'll just discuss this. The second part of the talk is really talking about some more experimental work that we've been doing to apply other data science approaches to mostly fine-tune notions of tempo and some degree of expression of dynamics. And some of the inspirations, there's everyone in the room has given a talk has inspired this to some degree, I would say, but certainly Keiko's work from the last meeting, very informative. There's also several papers like this in the realm of music information retrieval that compare that use data science methods or music information retrieval methods to compare acoustic recordings. So this is a fun study that compared acoustic recordings of a whole corpus of Beethoven symphonies to see how similar they are to each other in terms of dynamics and tempo and timbre. So you can see, Toscanini is kind of in a class by himself, and if you've heard his recordings, you know why. Whereas, Simon Rattle, depending on which orchestra he's with, tends to produce similar tempi and dynamics and timbres, interestingly. So and those techniques are the same techniques that it's this idea of hierarchical multidimensional scaling for comparing music performance styles are the same basic methods that are applied, that I've applied in this work that I'm going to talk about. Certainly, all of Peter's work. I mean, we're really building on the foundation that he set for us. And as Peter mentioned, all of this expression work, or all of the refinement of our player piano emulator, the Pianolatron, is building on work that Craig and then Kitty Shi at Stanford have done. Okay, to return to a very fundamental challenge with piano rolls. First of all, there's the issue of tempo and the speed of the roll, which, as we know, is not really constant or a set for any roll. It's always a choice. The roll might tell you it should be played at 90, which generally translates to like 9 feet per minute, but that's a pretty broad range anyway. And there's an additional complication, which is just that there is no pinch roller. There's no capstan system on a piano roll system. So as the roll builds up around the uptake spool, the actual roll movement speeds up. And this is something that people knew about, obviously, and it was factored into the recording process. But it's also necessary for us to know about it when we're scanning the roll visually and then emulating the playback of that roll. So it's something that we needed to emulate. Fortunately, we got a lot of guidance from Wayne Stanke on this. He pointed out, he gave us all kinds of equations that eventually were used to produce some good parameters for this emulation. But he pointed out that the key factors really are the actual initial diameter of the uptake spool, which will affect how the roll accelerates as it's played, and also just the thickness of the paper is a major factor. So these are interesting variables, and if you plug them in, you get a particular number. It's kind of like gravity, 9.8 meters per second per second. So you get an acceleration constant. But even then, there are other even for this, one of the most basic aspects of piano roll playback, there are other complications, including this notion of pneumatic droop, where the uptake roll is also getting heavier as the roll is playing, and so the acceleration slows down. This is actually some work of an experiment that Wayne did to sort of quantify how all this works out in practice. And so the data science approach that we've taken is just to take this experiment that Wayne did once and repeat it 100 times with a bunch of other rolls. Most of them provided by Peter through his reader system. But let's just get at some interesting questions of fairly basic music appreciation via rolls questions. So if you compare, these are many performances of the Liszt, Busoni, Horowitz, Figaro variations. So these are actual audio recordings of the rolls being played. You can see they differ in duration by up to a minute or so. And maybe a little bit less, actually. And over the course of 14 and a half minutes, it's somewhat perceptible, but there's also some interesting things that you notice looking at the waveforms where you begin to wonder whether the differences in the overall durations are due to just the differences in starting tempo or acceleration, actual behavior of the playback machine that's being used, playback or the scanning machine that's being used. So just to review the method that we can use, and that Wayne Stanky also described in his paper, to evaluate how the acceleration is unfolding during a playback. We have the roll that was played, or at least we think we do. Now, as Herman mentioned, maybe that's not earlier today in his talk. That's not an assumption that we can make lightly, as it turns out. We might think we have the same roll that was used to play back. It's the same recording, so we think it's the same roll that was used to produce a particular audio recording of a roll, but actually maybe it's a different edition and it's slightly different. So that's something to keep in mind. So everything here should be taken with a grain of salt. But given this assumption that we have an accurate scan, and it's the same scan, it's a scan of the same roll that was used to produce an audio recording of the roll being played back. We know the distances on the rolls that had to be traveled to produce the different notes. We can also just measure the time between those events as actually realized either by the scanner when the roll is being scanned, or actually by in the audio recording. So this gives us the two pieces of time and distance that we need to do this kind of acceleration analysis. And then we can do this for a bunch of rolls. Starting with Peter's corpus that he very generously has shared with us to make all of this emulation possible. And we can see we get, quite constant, except for that one, quite constant acceleration rates. There doesn't seem to be much pneumatic droop, but it could be because it's on an electric motor. But the difference that would make would be pretty minimal anyway. But we can see in practice, you see the acceleration happening as you're sampling these velocities across the performance. Then I occasionally get weird results, and sometimes they're legitimate, and sometimes you just chose a different recording of the same piece. So this is what happens when you have a mismatch there. These are those are all red Welte rolls. These are, and we also wanted to double check the acceleration constant for green Welte. And so here are some experiments where we've done that. Again, they're fairly consistent rates, mostly with Peter's scans. There do seem to be two kind of different rates, which I'm curious about.
Can I just correct myself?
Yes. Oh, yes, you want to use it?
When I did green...
Is it on?
Is it on? Hello?
Yeah, it's on.
Yeah. There is an error in my green acceleration, and it is due to the fact that I used the wrong size spool.
Okay.
It should be 7% faster.
Okay. So we're off by 7%. Okay. I'm not sure if that's what we're seeing here, or if it's just a difference in... there's some difference in, like, paper thickness as well. But it's very... Yes, it is, yes. With all of this, yeah. And which is one of the points that I'll try to summarize at the end, is that this kind of variety is to be expected and to some degree understood as part of how piano rolls work, as part of the core sort of aesthetic of the medium. And occasionally strange things, some interesting artifacts show up that you can look to more closely with particular rolls. You can tell us how this happened. So that's comparing scanned rolls to the actual distance measurements on the MIDI that's generated by scanning the roll as it's being rolled up to the actual measurements on the flat scan, basically. But we can do the same thing with audio by matching the pitch chroma of like an unaccelerated audio rendition of a roll with a regular playback, an accelerated audio rendition. And this is all software packages that are available. This is librosa, which is a Python package, but I think Sonic Visualizer does something quite similar. This is a little bit of that multidimensional scaling where you get a warping path that shows you how the unaccelerated and the accelerated playback compare to each other. And then you can derive these acceleration fits from that. And there's a bit more variation. I'm really curious about what is going on with the tacit audio recording that I think Hans Schmidt put together, which is my personal favorite, but it doesn't accelerate at all, or it accelerates up to a point and then doesn't at a certain point. And again, this is something we need to look into more. Yeah, it might have been an editing decision at some point, yeah, which produced a better performance, I think, but if that's the case. But that happens. Finally, we could even take just wildcat videos off of YouTube of someone playing a role on their home system, and we can determine, see what, well, first of all, we can see which starting tempi they chose, which is just kind of a curiosity, although eventually you could come up with a consensus starting tempo for every role if you had enough data for that. Then you can also see how the acceleration characteristics of these, maybe you could say amateur systems, although we're all amateurs at some level, are working. And so then you see other artifacts, and I'll actually return to this one at the end here in a few minutes. But given all this data, then what we've been able to do with it is to use it to inform how our emulator is put together, and actually to sort of more than, instead of dictating particular settings and not allowing them to be changed, we just we use these as a basis for default values for things like acceleration, but allow people, users, the option of changing them if they like. So these are the settings for, given all the roles that we've applied these techniques to, red and green Welte. Yeah, so this is kind of how that work has translated into our emulation setup. And just to briefly here, to highlight some kind of maybe emerging technology that can be used potentially more for getting more introspection into what's happening with the dynamic emulation. I'll mention that it is now possible, in addition to pitch chroma, you can actually just transcribe an entire polyphonic piano recording into MIDI directly using a deep learning model. Which actually doesn't produce very different results for this kind of question, but it's an interesting technology. This is AI coming for ear training classes anyway. So the model that works the best. So this is the original roll. This is kind of our rendition of it in MIDI. This is Carreño's Waldstein Sonata Movement 1, I think. And these are a couple open source models, including one from ByteDance, the TikTok parent company, that is able to transcribe all of the notes and the pedaling from just the audio. Yeah, and there's a bit more finger pedaling because it can't see the pedal. There's actually no way. It's just being inferred. I can show you how they do it in a second. There's also another model from Spotify called Basic Pitch that's actually pretty terrible for piano, but it's made for any combination, any polyphonic combination of instruments, so it works pretty well given that. Yeah, so how do these things work? Well, it's a deep learning model, so basically you just feed it a bunch of spectrograms of the recordings, and have someone produce MIDI renditions of MIDI transcriptions of both the note onsets and their velocity levels and the pedaling, and then you stick a whole bunch of gated recurrent units together. For the electrical engineers in the room might think this looks a bit like some kind of operational amplifier or something. So it turns out if you string together about 1 million operational amplifiers, you get artificial intelligence that's able to transcribe a live piano to MIDI. But you can see the accuracy is better for just onsets than it is for releases and velocity. It goes down to 80%, but the models are getting better. 92% accurate in pedaling, which is impressive given that it knows nothing about pedals. It's just being told a pedal is on here. When you hear something like this, it means a pedal's on. So these are some emerging technologies. This basically, all we've really used it for now was to double check this interesting artifact of Hans Schmidt's performance, rendition of the Liszt Busoni Figaro roll, to show that on the left here we have the initial acceleration and tempo analysis based on pitch chroma matching the sort of more music information retrieval traditional approach, and on the right we have the basically the same profile with a little bit fewer vertical outliers based on this, the ByteDance polyphonic transcription approach. So this really lets us just get at the details of what's going on with a particular playback of a roll. The potential here, which a lot of other folks have, I'll wrap up, other folks have alluded to, is that, so Harman's talk earlier today, and Craig and Akiko as well, we're talking about the potential of getting actual velocity levels of the audio recordings and using that to infer what's going on within the expression boxes of the player pianos. And apparently we also maybe even need to think about the fact that the treble and the bass may be calibrated differently for the players and for the actual recording instruments. So we can get all that data from this kind of work, but this is work that I'm certainly leaving for future work. It may or may not be something we pursue to enhance our emulator, but it might be. Oh, and then here's a just a visualization of a door. Yeah, it's a little bit of a mixed metaphor here, but just to show it is possible, to use some of this data to infer what's going on in there. I would say, at this point, it's better to have someone like Peter instrumenting the actual. Yeah. Okay. Yes. Yeah. We should go ahead. So, and this is just another example of how that works on a red roll and in our emulator. And finally, just to go back to that last example, what is happening at minute 12, or it's actually about 12:30 in the recording, where the tempo drops off suddenly. So I can actually just play the, if I can find the, all right, let's see. So just pay close attention when the timer gets to 12:30. You can see what happens to produce this drop in the audio, a drop in the velocity, or the tempo, I should say. So the video actually pauses to give you a little bit more of a dramatic pause. It was nice that they just gave us the video so we can see it happening. There was actually kind of a glitch later on in the performance where it pauses again for a very short time. So it's possible that wasn't intentional, but I think it was probably intentional. And I like it actually. So that's the kind of thing that you can you can derive from these approaches. So yeah, that's all. I'll leave this up here. This is information about our software. Thank you for your attention.
Look, I'd love to ask for questions, but I think we'll have to move on because time is running very short, and but look, I have to say what these guys are doing at Stanford is just incredible, and it's moving the science forward in a way that we as individuals could not do. And it's Bern University, it's people like Herman. We need this in order to really understand these roles and to keep them alive for future generations, to do all that sort of thing. So, Peter, I just want to thank you from the bottom of my heart, and I'm sure you do too. Okay, our next two speakers, where are they? Koos and Marcel. Koos is also a bit of a scientist. Marcel is a collector, and between them they have developed a number of very interesting things, but I'd like to give Marcel the opportunity. Marcel, would you come out here, please? And very briefly introduce what you are about a conference coming up in Leiden in Holland. It's a very interesting conference, and I'll just give you 2 minutes to introduce it.
Oh, that's more than enough. Thank you very much. My name is Marcel Veel. I'm the chairman of the Dutch Pianola Association, and next year we will celebrate our 50th anniversary. And to do that, we decided to make an event around pianolas and play the real pianolas. Although I think that the instruments we are using in this conference are beautiful, but they are not the real thing. I don't see a roll in that pianola. Come on. Okay, I cut it short. We are going to play 4 of those instruments, but we decided to add piano disc system 2, so we call the event the Big 5. It is September 11, 2025 it starts. There is a folder at the entrance of the conference room. Please take one. And we do all kinds of things with those beautiful instruments. So you're all welcome. Thank you very much. Thank you very much.
Thanks, Marcel. And I think it's important we do keep our feet on the ground about the original instruments as well. I have 2, and I love them. Okay, our next talker is Koos van Kruistum. And Koos has come to the interest fairly late in the last few years. He is, I think, by definition, an engineer. I've seen his work. He had a beautiful display at Bern with a wonderful means of reading rolls and of cutting rolls. And I think their work today is expanding even further. And as far as I'm aware, and I could be wrong in this, Koos, that you are working on ways of creating new rolls, that is, modern rolls for the Welte. But, part of what Koos has to say, I'm sure we'll find very interesting, the journey towards that, and well as what he's now doing. Koos, welcome.
Yeah.
Do you need a headphone?
No, turn it off. I think we're getting a loop for you.
Oh, no, from that because it's...
Oh, yeah.
Thank you, Peter, for the introduction. I put it some higher because I'm bigger. I'm taller. Thank you. What a very interesting conference. With beautiful people here in the Sydney Conservatorium Music Hall, in breathtaking country. Thanks to the group of people who made this possible again. And yes, very nice that we can talk a long weekend about pianolas. My friends know everything about pianolas. I could talk for 10 minutes and then I shut up. Good afternoon, ladies and gentlemen. My name is Koos van Kruistum, together with Marcel Veel. He sits over there. We create reproduction piano rolls at Welte rolls in the Netherlands. Last time in Bern, we shared what we had achieved so far, concluding with a performance of a custom-made Welte roll. You may remember that we gave away that roll, and that was then the rarest Welte roll on earth, because there was only one. Although we were proud of this achievement, this roll was actually far from complete. The range of elements needed to control this mighty instrument is somewhat technical. Instruments were not yet fully explored. This presentation is somewhat technical, but I have tried to keep it as simple as possible. Which steps are actually necessary to make a good Welte roll, or rather, to make the best possible Welte roll? I phrase it in this way because we realize that the music piece recorded on the roll is never played on the same instrument, so it's already different from the start. Despite the impressive result of many rolls, we must also realize that there are things a Welte simply cannot do. It's important to establish that. You need to think about how to bring the crescendo pneumatics into the right position at the moment the key is struck? And what is the right position of the pneumatics? If you start with a MIDI file, which is a computer file where all notes are recorded with timing and velocity, how do you know which velocity corresponds to which position of the crescendo pneumatics? This will have to be calculated using an algorithm. Is the speed of the Welte, where Peter Broadwell talked about, is the speed of the Welte air motor constant or not at all? What is possible and what is not? As is known, a Welte has a bass and a treble. That means we have one pneumatics for the dynamics of one half of the keyboard and the other pneumatics for the other half. Very effective if you play the melody in the treble and accompany softly in the bass. But what if a melody also needs keys that are high in the bass? Well, will they sound loud or soft? The position of the crescendo pneumatics tells something about the negative pressure in the key pneumatics when two keys are being struck at the same time in the bass or in the treble. In principle, they sound equally loud. But when we have a recording of a pianist who within one chord in the treble strikes with one key that sounds louder, that won't work on the Welte. There is some nuance that can be added, but I'll get later back on to that. Another problem could be when two notes that are so close in time and so far apart in velocity that it cannot be achieved. A choice will have to be made. During our quest to create the perfect Welte roll, we have discovered a lot, heard many opinions. We must realize that there is no perfect Welte roll, simply because the system has its limitations. But there are few systems that achieve such breathtaking results without having to be perfect. In Marcel's beautiful restored Blüthner Welte, which has been completely restored from top to bottom, a piano disc recording rail has also been installed. When a pianist plays a piece for us, it is recorded in MIDI format. If we use this MIDI file to create a roll, that would ideally be exactly the same as how the pianist played it. That would be technically the best Welte roll on earth. But what is needed for that? How do we get the Welte to the right volume for each note? What position should the crescendo pneumatics be at a certain MIDI velocity? How do we calculate that? First, let's look at how we establish the link between MIDI velocity and the angle of the crescendo pneumatics. When I strike a key, I hear a note with a certain volume, which I can measure and record in the computer. The recording rail emits a MIDI signal with a certain volume, which I also record in the computer. With a self-made Welte roll that reproduces a series of notes at an increasing volume, we record it in the same way. We measure the position of the crescendo pneumatics and the amplitude of the string. Now we have two tables. When we link these tables, we thus know which position of the pneumatics corresponds to which velocity of the MIDI file. But it was not all that easy. How do you press a key 100 times in the same way? How do you measure the exact volume amplitude of the string? To press a key with equal force, we use a stepper motor. With an arm with felt attached to the shaft of the stepper motor, we can press a key of the grand piano with a certain strength, velocity. To measure the volume of the tone, the amplitude of the string, we use a humbucker. This is a pickup element of an electric guitar. We measure the amplitude of the string, and we do this always at the same spot. This gives us an excellent reference measurement. During the playback of the test roll, which strike the same note as what we did with the stepper motor, we measure both the amplitude of the string and the position of the crescendo pneumatics. The angle is measured with an encoder, a type of motor that gives pulses when you turn the shaft, about 4,000 pulses per revolution. You can accurately measure the movement and determine the angle of the pneumatics. Now we have two lists we can match up, and this way the link between MIDI velocity and the position of the crescendo pneumatic is made. By the way, we have two beautiful top working Welte instruments on which we do the measurements. Let's look to the results of the measurements. The first graph is a manual measurement of MIDI output and the amplitude of the corresponding string. The green line is the result of the MIDI velocity and the red line is the output of the humbucker. Later on we used the test with the stepper motor for this to get better average of the measured value. The second measurement is a computer measurement on a Welte. Here the crescendo holes and a note hole are opened with an electric valve, and the position of the crescendo pneumatics is measured. The graph starts with the crescendo forte. It is clear to see that the pneumatics does not go beyond about 17. We call this the crescendo maximum. Then comes a sforzando forte right behind it, and then the pneumatics close completely. I will get back to this later on. If we look at the movement of the pneumatics, we see two movements, a fast movement and a slow movement. The pneumatics moves from one position to another in fast or slow way. We look at these movements in time and see them as two different lines, each with a different directional coefficient. When we examine the ascending and the descending movement, we also see differences here. The pneumatics opens faster than it closes, faster, softer, than louder. Sorry, the pneumatics opens faster than it closes, faster, softer, than louder. What is very important when calculating these moments is that you must take into account that there is a minimum hole size. Sometimes a half a hole comes out much better to reach a certain position, but we have never seen a half hole at the Welte roll. For the next 3 slides, the same applies. The start of the graph is the velocity of a note or a calculated velocity, and the end of the graph is also a velocity or a calculated velocity. The lines are the movement of the pneumatics. This is a simple example of a dynamic change between two notes. At the beginning, a note with a velocity of 45, and at the end, a velocity of 80. You can see clearly that the space between the notes and the velocity difference that must be bridged is spacious enough. The blue line is the slow movement of the pneumatics, and the red line is the sforzando forte movement. The time the red line takes must be at least 1 hole size. This movement is a bit different. At the beginning, a note with a velocity of 58, and at the end, a velocity of 40. The blue line is decrescendo movement, green is the sforzando forte movement, and red is sforzando piano movement. Here too, you need to take into account that the minimum hole size for the red and the green line is just 1 hole. This example is a bit more complex. The graph starts with a note and ends with a calculated crescendo moment. The note falls halfway through a sforzando hole. You can see now that the last moment is no longer exactly on the note, but comes a bit later. For the calculation to the next note, you must therefore be taken in account. Of course, it shortens the time for the dynamics to the next note. Let's take a look at the operation of the pneumatics and the notes in a Welte. In the picture on the left, I would say like this, you can see. Okay. In the picture on the left is a piece of a roll, this part. On this piece, we see three notes, CR1, CR2, and CR3. These notes are struck shortly after each other with different velocities, respectively 69, 73, and 75. The blue arrow points to the direction where the paper moves to. When the first note, CR, is struck, the pneumatics is in a position that corresponds to a velocity of 69, this point. We call this crescendo moment 1. Simultaneously with this note, a crescendo forte hole starts here. Lost where I am, but I will find it. Starts. The purple line in the image shows how the crescendo slowly grows, and that's the slow crescendo forte. To reach crescendo 2, a sforzando forte hole must be started at the right moment so that the pneumatics are exactly in the right position to reach the velocity of 73 when the note CR2 is struck. This moment here, the sforzando starts here at this point and ends here, and the note is struck here. Because the hole continues, the pneumatics will further close crescendo until crescendo moment 2 is reached, and that's at this point. However, there is something else going on. The orange dotted line shows the maximum value of the crescendo. In other words, when a crescendo forte hole passes, the pneumatics remains at this level due to a spring on the outside of the crescendo pneumatics, in which case we are dealing with a sforzando hole which goes through there. Because the spring pulls the direction coefficient of the ascending line changes. At crescendo moment 2, the sforzando hole has passed this point. And the decrescendo hole appears directly. Due to the spring, the pneumatics will first open quicker to the maximum crescendo velocity and continue to open more slowly. So what you see here is at this moment a crescendo piano starts, and it does not have the same angle which it has under the maximum crescendo velocity. So it drops faster at the first moment, and then when it's under the maximum crescendo velocity, then it takes the line, the normal line. Finally, a sforzando piano hole is timed so that when the note CR3 is struck, the crescendo is exactly 75. When this hole is passed, we reach crescendo moment 3. This all happens within 100 milliseconds. Okay. This is an example of a Welte roll during one sforzando forte hole. 3 notes passed with all different start times and therefore different velocities. In our Euterpe collection, we have 1650 Welte T100 rolls, scans. There are only 5 rolls where no notes are played during sforzando holes. So the other 1645 rolls has notes that are being played during a sforzando hole. Timing within a sforzando hole is crucial. A fraction later or earlier and the note is too loud or too soft. How this was managed by Welte is a mystery to me. That this has been done manually by an editor seems impossible to me. Maybe a computer from the future with AI is sent to these guys. We will probably never know. As Welte himself said, ganz einfach. Pedal time is certainly also very important. When a pedal time of the sustain pedal does not match, it can completely ruin the performance of the roll. Equal important for the soft pedal, but less audible in the performance of the roll. With a reproduction piano, it takes a while before the pedal is fully operational. We have measured the pedal times with the encoder also. The ratio between key and hammer time must also be taken into account. The speed of the hammer, which with louder notes is faster. So when the pianist strikes a chord of one note, where one note is louder, that would actually be impossible on the Welte. But in a louder note, the hammer reaches the string faster. When the loud note is struck in time slightly later, it is possible to make an audible nuance in the velocity without the notes sound separate from each other. We have extensively tested this. A louder note may be struck 40 milliseconds later without this being perceived as disturbing. The result is that when the chord plays, a velocity of 50 sounds louder and is played by 58. Regarding to the speed of the roll, and that's what Peter Broadwell also told, there are 2 things to consider. These are the paper thickness and the decreasing speed when the roll is being played. When the roll is played, the diameter of the roll will grow 2 times the paper thickness. With each revolution, the increased to the throughput speeds of the paper for a roll of 45 meters long. The initial speed is 9.8 foot per minute, and after 45 meters, it becomes 11 foot 65 per minute. The holes must therefore become respectively longer and further apart. Logical. The speed of the motor also plays an important role. As the roll is wound, it becomes a bit heavier for the motor, which results in a slowdown of revolution per minute of the motor. The motor starts with 118 revolutions per minute and ends after 45 meters at 114 revolutions per minute. It's easy to calculate what the final acceleration is. I haven't said anything yet about the mezzoforte hook. Playing with the mezzoforte hook on, in my opinion, was never the intention. A pianist doesn't play at one level either. Welte is a floating system. Only when the minimum or maximum value is reached, then you know exactly what the position of the pneumatics is. We call this phenomenon clipping. With the calculations of the velocity, it's constantly whether there is time to clip, because if you have done that, then you know exactly what the position of the pneumatics is, and the calculations will be more accurate. Clipping always happens downwards. Then the movement of the crescendo pneumatic is calm. The hook also becomes very handy because when the playing is loud, the way to clipping is shorter when the hook is on. If louder notes are played, the Welte T100 also has a function to speed up the motor. This creates more negative pressure and reduces the chance of failures. We have also devised an algorithm for that. In short, everything starts with an instrument and a pianist. With today's technology, it has become fairly easy to accurately capture the pianist performance. This performance is stored in a MIDI file. To use the MIDI file to operate a Welte, some calculations must be made to produce a roll with Welte can work that the Welte can work with. After that, we can sit down, lean back, close our eyes, and listen passionately to the pianist once again, and again, and again.
Well, I found that particularly fascinating, given I live in the same crazy area that Koos does. Look, we don't have a lot of time for questions, maybe one or two. Craig.
So how are you, when you're producing a paper roll, so for modern performance, maybe you don't need quantization in time anymore. Do you have quantization or is it continuous?
We don't have quantization. We correct the acceleration for the length of the paper, I think just like Welte did.
Oh, so you have an acceleration in your playback?
Yeah. When you have a MIDI file, it's just the time that the pin is played. Yeah, yeah. So that it the time of the roll is exactly the time of the MIDI file.
Yeah, so even better than your
You can understand the difficulties, I think, of trying to translate something made in 1905 into something that we're trying to recreate in 2024. There are many mysteries, and I don't know we'll ever get there, but we can get close. And it's one of the beaut things of this conference. Herman.
Yeah, so I was fascinated by the method you are using. So last year I have got a lot of conferences about embodiment in performance. What it means is performers try to make the same performance with the body as former performance did 100 years ago. In your case, your Belgian is a body.
Yeah.
You make a new embodiment for how recording could be made 100 years ago, and so I really think there's a lot to learn from it, and so I thank you very much for the presentation.
Thank you. Well, look.
Thank you very much, Koos. Very interesting. Now going to welcome the next scientific person, although he's not really scientific, and that's Kumaran. Kumaran's going to talk about the Pianolatron, which Stanford University has been producing, and I assume demonstrating it on the disc clavier.
Yeah.
So without any further explanation from me, I'll hand over to Kumaran.
Thank you. Let's see if this works here. What do we do here? The laptop?
It should be right.
Okay.
Yeah, laptop is right. Okay, it's
There we
taking
go.
a minute too. Yeah.
Okay. And then
Alright,
do we have to mirror the screen?
yeah, so I would drag this over. Yeah. Yeah, let's just
Okay,
do this.
that's
Right.
good. Yeah, and then we can maybe maximize it.
Yeah,
I'll just put the
yeah.
green dot, yeah. I'll have to use
use it there, so we'll keep that cursor there. Good. Okay, yes, I'm definitely not scientific. This is definitely not me. But I'm very grateful to the genuine scientists whom we are very reliant on, like Peter here. So I'm actually showing off Peter's work, in effect. Although what I do is I basically tell Peter what I would like to do, and then he sits slaving away at it and creates it with months of work. So I feel sort of unjustified in showing it off myself. It's really his baby. But in any case, we dreamed this up years ago, and I know I talked about it in the last conference, so it might seem strange to mention it again, except that so much development has happened over the last 2 years, and so I just wanted to introduce it again, so to speak. But it is also, I should say, still a work in progress, so we are not yet fully ready. We have sort of high aspirations for this app. So just to go over what it is in a nutshell, just for those who don't know from last conference, it's a little bit novel in a few important ways. It's a JavaScript app, web-based, that can be accessed by any computer browser and with anyone with an internet connection around the world, and it'll allow for synchronized playing and viewing of the roles and varying degrees of interaction from very basic listening to advanced research capabilities. As an online player, it also allows any institution with some planning to display their roles on this application as well. And as such, it could become a tool utilized by other institutions as well, researchers and enthusiasts around the world for their collections and scanned roles. So let me walk you around the app a bit. But first, I should also say, given some of the topics of conversation this morning, that this is definitely a philosophy, you might say, of the role reproduction, which involves accepting it as an iterative process and a creative process, no reproduction exactly the same. And so we're basically involving the public and researchers in this process of reproducing roles, in effect. So here we have this. There are many people to thank being involved. This is Craig's group, partly, and music at Stanford. And Cider is Peter's actual group, and the Stanford Libraries, whom we have very many members of here. I should definitely thank them. Nathan Coy, Tamar Barzell, Jill, and many others who are all involved with making this happen, the immense amount of pipeline work that has to go on the backside to even get these scans up there, to get the roles accessioned and so forth. We can search for the different types of roles that we have here. We just have a small subset at the moment, but we have some 415 Welte roles, which have been up there on Supra for a while, and some other ones. Then you can see over here on this side, we have the play, if you just wanted to play the role, and then we have a user interface for actually interacting. I'll show you that in a moment. You can download the MIDI file, the expression MIDI file and the raw MIDI file, and also view a image. You can download images of the role too, in various degrees of resolution. So all of that is access for the role collection and the role scans. Let's see here. So, of course, the utility of seeing roles shouldn't be underestimated while they're being heard. And we've typically accessed roles by listening to recordings of them, but we know there are a lot of values to listening to roles. And of course, you can see the holes, you can see the leader, you can see the punches, and you can see any marks and notations on the roll, of course, for those researchers who want to do that. And then, of course, there are things like the audiographic rolls, which are very special. So this is an example of that, the Stravinsky Firebird. And I'm going to be playing it here, and we also have a capability at this point to play this web-based app on any MIDI-capable instrument. So that includes a disc clavier like we have here. We've connected it. Hopefully it'll work. If you don't have a MIDI-capable instrument, it would just play it through a sound sampler on the computer, which is built in, so you can hear it still on the computer. But if you do have a MIDI-capable instrument, it'll sound better, hopefully. So let's see. Here you can see the markings, of course, annotations. Okay, I'll leave it there for the moment. In any case, obviously that's a very neat thing to see and hear the roll together. Yeah, yeah. Yes, it does this actually. Yes, the pedal is still down for the moment. We'll hopefully... Is that right? What do I do?
We can also just mouse over. If you just mouse over the pedals down here, it should work.
No, I do. Can I mouse over this? Yeah.
Okay, that one should go up. Now this one too. There. Okay. Yeah. There, okay.
We have pedal commands. Yes. By the way, these play notes. You can see the key here. This is like a MIDI capable keyboard, so you can actually see the notes. Anyway, let me move on. We have very little time. So, of course, this is more than just a playback mechanism and seeing the rolls. We have these adjustments here. You can view it without those adjustments, by the way, for reproducing rolls, so that people don't have to get involved with involving themselves in the roll production. If they don't want to, they can just hear it, especially if there are expressions already on the roll. But if we wanted to get involved, as many of us do, make a little adjustment. So even something like this, a Hupfeld roll of Carl Reinecke, which we know is probably originally a phonola roll without expression on it and then added later and minimal pedaling and so forth. And so when you hear it, normally, it might... Okay, so it's not sounding too bad on the piano, actually. On the player app, it sounds a little worse, but we can, with a slight adjustment, if we were to go back to the beginning, you could reduce the bass volume. Just to show you the sort of distortions that are possible. Yes, okay, I'll get that again. In any case, let's see, how do I get the pedal app to come here? Go there. Oh yeah, I can just click that. Okay. So in any case, of course we could do sort of horrendous things with these rolls, but they often need little adjustments. So when we have problems with bass level dynamics, so there are other ways you might even address the emulation algorithm, you might say, with just general bass compensation. And we do adjust that in the emulation algorithms as well. But there are lots of small adjustments that can be made, and that can also be made relative to the instrument. So if the instrument happens to be poorly voiced in the upper register and it needs a little bump up, you can just bump up the treble range and have some compensation potential. And of course, you can get into tempo flexibility. That really is applicable to another critical feature of this, which is that it's also now allowing us to involve ourselves with pianola rolls, 88-note rolls, like we've heard wonderfully played out in the hall. And so this is a new capability, I think. And you know, it's a complicated interface. Right now I'm just using the keyboard. We do have game controller accessibility, so you can use game controller, hook up to this, and then you can control the buttons that way, which is actually a little bit more organic and a little more dynamic. But in any case, you can also do just basic things. Here I'm just going to play to start off. So that's what it would sound like normally. There's no pedal here, or it didn't come out anyway. So we can add pedal. I'm just using the space bar. And also that tempo seems a little slow. So if we just bump up the tempo a tiny bit, and then you play this now. Yep. Okay. So, so the point is that this allows you to play pianola rolls, 88-note rolls, which I think is a really big improvement in functionality for MIDI pianola rolls, 88-note rolls, which have no expression, of course, and that's a big downside. Rex has been complaining about this for years. So hopefully it's not, while it doesn't have the physical resistance of a push pedal, and people have thought about that actually, how we can model that, but that's coming maybe. But at least we have this functionality to actually engage with the roll now, which is a huge improvement. Also, I should say with classical rolls, if you were to do something like what Rex is doing, super nuanced interpretations, which is of course a very advanced piano list, you could say, there are ways we can deal with that too. This little excerpt here is a Hungarian Rhapsody in an 88-note roll. It has no expression on it. So that little moment here. And what you can do is actually repeat a section, so you can practice. We hit this little button there. Okay, that's the boring non-expression version. We can repeat that little segment now and practice it. So if I play it now, I'll try doing some tempo mod. So I tried to do a little bit there. This is not a polished performance by any means, but yes, sustained. But you can definitely do things with this. There's a lot of potential here to work on pieces. Also, by the way, that little excerpt can be, this is a research application, can actually be bookmarked. You can send this little excerpt as an embedded moment into to another person. So it could be embedded and also excerpted and studied online. And as well, you can make a recording of your performance here, if we were to do this. And then you can actually finish that recording, and then you have to export as a MIDI file, a WAV file, or you can actually keep it in the buffer and so forth. So you can make a recording of yourself playing, and then send that to other people as well. So I see we're moving along here. Just let me make one quick point, Peter. So this analysis, and we were talking about this earlier with Herman and so forth, the expression rolls, the expression lines on these rolls here can actually be emulated in our app as well. And so of course we can do excerpts, but right, he plays an A natural, and we can test here. It should be an A flat. And so that note can be examined. You can study that. You can repeat that. You can also see where the expression holes line up with that note. But in addition to that, another... Oh, yes, sorry. Absolutely. Sorry about that. That's a new problem for Peter to solve. So anyway, we can go to this in-app expression, and you can see the, in this case, the Welte green expression, and you can actually generate the velocity curve for that expression. So you can actually track it, like what Herman was doing, and compare our velocity, our emulation algorithm, to the one that's on Welte's curve. You can see there's some differences, and you can also adjust them here. So if we were to fiddle with this, just to do an exaggeration here, if I reduce the fast crescendo, you can see it gets much louder, changes the velocity curve. So you can see the impact of the different expression algorithm settings and how it would actually impact the expression. So anyway, we'll wrap up.
Weren't you going to continue over lunch?
Right, so what I'll do is, actually, yeah, we should go to lunch because we don't want to have cold lunch. But I will just, at some point, anyway, we heard it. We can play a lot of rolls. I was planning to just play a little bit of a Liszt Stavenhagen roll, but you can see what it can do. And the potential for it, I think, is quite significant. We'll keep developing it. It's technically not launched. We haven't opened it up to the public yet, although we're happy to get user feedback. So if people are really actively wanting to help us develop it, we'd send them around. And then we can develop a dialogue and so forth about it. But yes, I think
Sustained.
so. It's still there.
Turn it off. Yeah.
Great. Okay. So I think we'll stop there. And then if you wanted to come up and take a look at it, you can do that for a few minutes in the break. So thank you. Yeah.
Amazing.